Greetings, grade 11s and grade 12s, and welcome to Butu Academy, Lessons That Empower. We are still on the topic on Newton's laws and applications of Newton's laws. And today we are officially starting with one of the laws, and that would be Newton's first law. Now that we've cleared the understanding on forces, because that's what we are going to need to apply when we study all the four laws, okay? So today we are going to be looking at the first law. Before we go straight into the first law, the first thing that I would like us to do is to do a little bit of a recap of what we know from the topic on vectors in two dimensions, okay? Now the first thing that I want us to look at is what is referred to as the resultant vector, or the net vector, or the net force. In our case, because we are dealing with forces for now, we are going to be looking at the force only as one of the vectors that we studied in vectors in two dimensions, okay? So now we need to have an understanding of what is meant by the word net force or resultant force. Now, if you look at the definition of the resultant or the resultant vector in the topic on vectors in two dimensions, it says it's the sum of two or more vectors acting together. So in our case, because we are here dealing with force, the word net force, as you can see, the word net there, or the word resultant, means the sum of all vectors acting along the same line. I'm going to break down this definition into two. The first part has to do with the sum of all the forces, and then the second part has to do with along the same line, okay? Now, the first thing that I want us to understand is the word net. Please understand that the word net in physics and in mathematics, net and sum go together, and what they essentially mean is that you are adding, okay? So if you see the word net or the word sum, you know that it means you will be adding a few components together to get your answer. So the resultant or the net force is actually the sum of all forces acting together. What that means is that in order to get this net force or the resultant force, we need to add all the forces. So F net, as you can see there, F net is calculated by adding all the forces acting on an object along the same line. I'm going to explain the concept of along the same line just now. But for now, I want us to understand when we see the word net or the word sum, we must understand that it has to do with the calculation of adding. It means there are some additions that will be done. We'll be doing some adding in this case. All right. So to get the net force, we are required to add all the forces acting on the object. But now let's then understand the second part of the definition, which says along the same line. Okay. In vectors in two dimensions, in that topic, you were taught that you can only add vectors that are acting along the same line, or what we call the collinear vectors. So even with the force, because a force is a vector, anything that is applicable to vectors is applicable to forces, because forces are vectors as well. So you cannot add vectors, or you cannot add forces that are not going in the same line or are not acting along the same line. In other words, you can only add vectors or forces if they are going to the same direction or they are going in opposite directions. That's what it means to collinear. Collinear means along the same line, meaning either they are acting in the same direction or in opposite directions. So you can't add, for instance, you cannot add, if you have a vector here, let's call this vector 1 or force 1, and you also have force number 2. You cannot add those two because they are not acting along the same line. And we can see the other one is in the vertical axis and the other one is in the horizontal axis. So you cannot add vectors that are not collinear, because these two vectors are not collinear. They cannot be added. However, if you were to have a force, I'm going to use a different color here. If you had to have a force, let's say this is F3. Now, F3 and F2 are collinear forces. Why? Because they are acting along the same line. They are going in opposite directions. Okay, even if F3 was going to the right, it would still be added to F2 because they are acting in the same direction. That means they are still collinear. However, you cannot add F1 and F3 because F1 is in the vertical line and F3 is in the horizontal line. They are not collinear. We can only add vectors that are collinear, or vectors that are acting in the same direction or opposite direction. Okay, and that's what it means when we say vectors are collinear. It means they are in the same direction or in opposite directions. Okay, just remember that when you apply the laws of Newton, all three of them, especially the first three, you'll see that you cannot add vectors that are not acting along the same line. It's impossible to do so. Just like you do in mathematics, you cannot add x and y. You can add x and x, you get 2x. The same thing with the y values. They can only be added if they are in the same line or in the same dimension. Okay, next, the other thing that you need to understand is that if you have two vectors going in opposite directions and you need to add them, because they can be added since they are collinear. If they are going in opposite directions, it means they are collinear, therefore they can be added. One of them, if you have two of them, here we're using an example, if you have two forces and they are going in the opposite directions, one of them should be allocated a negative sign. This is to show that the two vectors cannot add to a bigger value because they are opposing each other. Okay, in other words, they are cancelling each other out. If they were equal, they would cancel each other out and you'd get an answer of 0. But if they are going in the same direction, they have the same value. If it's a 7 and a 3 Newton force going in the same direction, you just say 7 plus 3, you get 10, because now they are going in the same direction. It means they have the same effect in terms of direction. However, if the 7 Newton vector is going to the right and the 3 Newton vector is going to the left, the magnitude of the resultant, or the magnitude of the net force, will be 4, because the 3 will be cancelling 3 from the other vector, and then you'll be left with 4. Okay, so to get a correct answer in this regard, you have to make sure that if the two forces are acting in opposite directions, one of them is given a negative sign. This is where you have the liberty to choose which side or which direction do you consider to be negative. And it is considered to be good practice, and it also helps the person who marks your script to indicate before you do the calculation which direction did you choose, or did you opt as your positive direction, or which one did you opt as your negative direction, so that we can see why you put a negative sign on which vector, and then it becomes easier for us to read your script as well. Okay, so let's say let's look at a worked example. For instance, in this example, you have three vectors or three forces which are vectors F1, F2, and F3. There's F1, there's F2, there's F3. These vectors, as we can all see, they're either going to the same direction. As we can see, F1 and F2 are going to the same direction, and F3 is in the opposite direction. Therefore, because we have same direction and opposite direction, it means these vectors are collinear. Therefore, they can be added. If in this case you are required to calculate F net, in this case, you're going to say, okay, F net, remember net means the sum, which means to add. Okay, to get the answer, you're going to say F net is equals to F1 plus F2 plus F3. Okay, remember what I said about the direction. It is good practice to indicate which side you choose to be positive. Okay, in my case, I'm going to choose to the right as positive. You can write it in words and say to the right as positive and to the left as negative. So I know that any force that is negative, that is to the left, must be allocated a negative sign, and the one going to the right will be expected to be positive. Okay, in our substitution, we have to now bring in the signs as well. Okay, when during calculations, as you can see, during calculations, we must put a negative sign for the one of the directions. Okay, F1 is to the right, therefore it will remain positive, so it's going to be 15 plus F2, which is also going to the right, is equals to 11, plus F3 is to the left. We've chosen to the left as negative, so we're going to put negative 18 here. Okay, so if you prefer to be safe and use a calculator, which is what I know you guys prefer doing, okay, in this case we are going to say 15 plus 11 plus negative 18. Okay, so it's 15 plus 11 plus negative 18, and our answer here is positive 8. As you can see, since the answer is positive, it therefore means the resultant vector, so the answer here is positive 8 newtons. Because the answer is positive and you've chosen to the right as positive, therefore it means this 8 newtons is the magnitude, and therefore your F net, since it's positive, it's to the right. Okay, to the right, because as you can see, you chose to the right as positive and to the left as negative. This is just a recap. I know you guys know this, but it's important for us to keep this knowledge. Don't forget anything that you've learned. It's very important because physics builds up on top of previous topics that you've learned. So don't just learn and forget. Make sure that you remember the skills that you learned in previous lessons. So the skill of understanding the net force or the resultant vector is also applicable in other topics as well. So you'll see that as time goes on, you'll be asked to remember things that you learned in previous lessons. Okay, now let's look at Newton's laws. Okay, we've been waiting for this. I know you guys were impatiently waiting for us to start dealing with the laws. Now today we are going to be looking at Newton's first law. Most of the time, learners actually assume that Newton's first law is just a definition and then that's it. But unfortunately, it's not just that. And it becomes important when you learn the second law and the third law. The first law is also very important in terms of calculations. You have to have an understanding of what actually is meant by the first law. Now, by definition, according to our exam guideline, together with our CAPS document, Newton's first law of motion says a body will remain in its state of rest or more motion at constant velocity unless a non-zero resultant or net force acts on it. Okay, let's absorb that information. We have to break down this statement into a meaningful statement, because for now it's just a definition. Okay, so here we are told that if you have an object that is not moving or is moving at constant velocity, it will remain in that motion or state of motion. If it's not moving, it will keep on being stationary or not moving. If it's moving at constant velocity, it will keep on moving at constant velocity unless something happens. And that something is unless a net force acts on it. And that net force must not be zero. Okay? And you'll see what we mean by a net force that is not zero. So basically what Newton was saying here is that if an object is not moving, to get it to start moving, you must apply a force which is not zero. A net force that is non-zero must be applied to the object so that the object can start moving. If an object is already moving, but it's moving at a constant velocity, in other words, it's moving at a speed or a velocity which is not changing. In other words, let's say you have an object moving at 20 meters per second all the time. It's not changing. If you want the velocity of that object to decrease or increase, or maybe you want to stop it, or you want it to accelerate to a higher velocity or a higher speed, you must apply a net force, and that net force must be non-zero. In other words, that net force must be unbalanced. That word is also evident in some documents. You'll see they'll say a non-balanced resultant force. Okay, now let's look at what is implied by Newton's first law. Now that we understand, we've broken it down into its meaning. Now let's look at the details of what Newton's first law actually teaches us. The first thing that this law is teaching us is that for any object that is not moving or stationary or at rest, remember this is physics, and in physics there are some words that mean something else in some languages or some subjects, but to us they mean something else. Okay, we know the word rest means an object is not moving, or stationary, it means it's not moving. What that means, if an object is not moving, it means its F net is equals to zero. I want you to absorb that. Okay, if an object is not moving, it means all the forces acting on that object at that time are balancing each other out. Therefore, they are cancelling each other out to get a sum of zero. And I'll also explain something with regards to this just before we finish this slide. Okay. Also, this means that if an object is moving, okay, now you have a moving. Remember with the previous point, we are saying if an object is not moving, the net force or the total, the sum of all the forces acting on the object are adding up to 0. Now, if the object now is moving, but it's moving at a constant speed, you'll see this a lot in some of your assessments. It will say constant speed or constant velocity. Remember, velocity is similar to speed. They're not the same. They're similar. Speed is a scalar quantity. It does not have direction, whereas velocity has direction, is a vector quantity. If you are told that the object is moving, but it is moving at a constant speed or a constant velocity, again, that means that all the forces acting on that object add up to 0. Those are the forces acting along the line of motion. Okay, so this is an object that is moving, but is moving at a constant speed or constant velocity. Therefore, F net will be 0. So this is important when you read statements. If you come across a question and they say, here's an object and is moving at a constant velocity, immediately you register that into your mind and know that, okay, if this object is moving at a constant velocity, it means the F net for this particular object is 0. Okay. This, however, this means that for any object at rest or object at rest, like I said, it means an object that is not moving or moving at constant speed or velocity, all the forces acting along the same line will cancel each other out. Okay, let's explain what that means. This is the part that I spoke about earlier on. We are saying that Newton's first law is saying that if an object is not moving, okay, it means if there is a force going to the right, let's say there's a force going to the right, we're going to call it F1 is equals to 10 newtons is being applied to this object. It means there is another a force acting to the left, F2, which is also equals to 10 newtons, because the F net for this particular object will add up to 0. How do we add up to 0? If you choose one side to be positive, what you get is that your F net here will be equals to F1 plus F2. And if you choose to the right as positive and to the left as negative, what we get is that this will be 10 plus negative 10. Okay. And what does it add up to? It adds up to 0 newtons. Okay. That's what it means. It means that these forces are cancelling each other out. Okay. Right. This means that these forces are there, but they cancel each other out to give us an F net, which is equals to 0. Okay. You will see even in my next point here, what I've explained is that this does not mean that there are no forces acting on the object. When an object is not moving, or when an object is moving at a station at a constant speed or a constant velocity, that does not mean there are no forces acting on the object. Hence, I wrote this even in capital letters. Please remember that. When we say F net is equals to 0, we are not saying there are no forces acting on the object. We are saying if there are forces acting on the object, they are equal to 0 in terms of their sum, or the sum of those forces is equals to 0. F net is equals to 0 because F net is the sum. Okay, we add all the forces acting along the same line and we get 0. That's why the object is not moving, or that is why the object is moving at a constant velocity or at a constant speed. Okay, the example that I made just now has to do with this line here. As you saw, if an object is not moving, and we have two forces acting on that object, it means the two forces have equal magnitudes but opposite directions. That's why when you add them to get F net, you get 0, because the other one will be positive and the other one will be negative. And we add the positive and the negative, we get 0. Hence, we say F net is equals to 0 for all objects that are not moving, or for all objects that are moving at constant speed or constant velocity. All right. Here's a worked example similar to what we've just dealt with just now. Here we have a mass block that is dragged across a rough horizontal surface. We know rough horizontal surface. We've already learned based on the forces that we did that this means that there will be a frictional force when you see the word, especially the word rough there. Now it's being pulled by a pulling force. A pulling force, remember when we did forces, it means this is an applied force. Okay, excuse me for this. A pulling force is an applied force. So there are two forces here acting on this object. So the block moves to the right at a constant speed. As soon as we see the word constant speed, we remember Newton's first law. Newton's first law tells us that if an object is moving at a constant speed, it means the F net there is equals to 0. Okay, so basically what this means, if this was there was a free body diagram, this is why free body diagrams are extremely important, especially for your calculations. It means this is an object that is moving to the right, therefore it means it's being pulled to the right by Fa, and there is a frictional force. Of course, because this thing is moving to the left, it means the frictional force will be a kinetic frictional force, and it must be to the left. Why is it to the left? Is because the object is moving to the right. Okay, so the applied force here is 75 newtons. Okay, and we know that this object is moving at a constant speed. The question is saying calculate the frictional force. The frictional force is what we do not know. That is our unknown force. But what do we know based on this statement? Constant speed means that F net, okay, constant speed means that, what have I done here? Okay, constant speed means that F net, let me just fix this. Okay, constant speed that means F net is equals to 0. But what is F net? Remember, F net is not necessarily one force. It's a combination of all forces acting along the same line. What are those forces in this case? It's Fk and Fa. So when we do our substitutions, we need to consider one direction as positive. If I choose to the right as positive and to the left as negative, then I substitute. I say, okay, I don't know what Fk is equals to, but I do know what Fa is equals to. Remember, F net is actually equals to Fa plus kinetic friction. Let me just put it correctly here. Kinetic friction. The two of them added together are going to give us 0. When we substitute, we then have Fa, which is 75. It's positive because it's going to the right, plus Fk, which we do not know its value, is equals to 0. If you transpose, what we get then is that Fk is going to be equals to negative 75. What does the negative mean? Okay, we get a negative answer. The negative is telling us, remember, we chose to the left as negative. The negative is actually telling us the direction of Fk. Okay, so this, you don't stop here, and we see this a lot where learners stop here and said they actually put a unit there and say, I'm done, therefore I've answered the question. No, you have not answered the question, because the question is say calculate the frictional force. Remember, a frictional force is a vector quantity, and a vector quantity must have a direction. So your final answer should be, therefore, Fk is equals to 75 newtons to the left. I don't have enough space here. I'm just going to, please excuse me for that. It must be to the left. How do we know it's to the left? Is because we had a negative answer here. The negative answer is telling you that this object is moving to the left because you've chosen to the left as negative. All right. So when you substitute here, another common mistake that we see learners making is that they would substitute Fk. When on the substitution here, they would correctly put a 75 there, and then they'll put a negative Fk. Now the problem will be, if you do that, you're going to get an answer which is positive, which is might mislead you into thinking that a positive answer means this, or this force is to the right, but we know that this force is to the left. So don't make that mistake. I would really advise you that you just substitute Fk as it is, and you will get a negative value. The negative value is telling you that this object is moving to the left because you've chosen to the left as negative. Okay, I hope you have an understanding there. In a nutshell, that is what Newton's first law is about. It's telling you that if an object is not moving, it will remain in that position of not moving unless a net force acts on it. That net force must be non-zero, which means it must be unbalanced. In this case, you see Fk and Fa are actually balanced, so the F net for those two is 0. So if you want to make a stationary object to start moving, you must apply a force that is not balanced by any other force. Okay, the other thing is that if an object is already moving but is moving at a constant velocity or a constant speed, to change its speed you must apply a non-zero net force. But remember, net force is not necessarily one force. It's a combination of all forces acting along the same line. So to get F net, remember, we calculate it by adding all the forces acting along the same line. Yes, it does happen in some situations that you find that F net is actually just one force, because there's just one force acting along that line. So F net will be that one particular force. Okay. Let's move to a little bit of theory now. In your exam guideline, you will see, together with the ECAPS document, you will see that you have to understand the concept of inertia and the importance of seat belts. Okay. Firstly, the exam guide defines inertia as the resistance of an object to any change in its state of motion. This is actually linked to a certain extent to Newton's first law. Okay. An object usually will resist the change in its state of motion, even when there is a force intending to do so. So usually, this topic is actually assessed as a theory. They'll ask you to define what inertia is, and they'll also ask you to explain why we need seat belts in our daily lives. Okay, when traveling in vehicles. So when you are in a moving car, this is just a quick explanation. If you are in a car and the car is moving, basically your body, which is you, is moving with the same velocity as that of the car. And that some of many of us have experienced this, that if the car suddenly or stops abruptly, in other words, the stopping of the car is not so smooth, you will actually feel that your body wants to keep on going forward. You see? If you remember Newton's first law, what we did in the previous slide, you'll remember your body will want to continue in its motion. Okay, so your body will still continue to move forward due to inertia. Remember, inertia is the resistance. So your body will resist to stop. If the car stops, the body will resist to stop because of the inertia. Your body will want to keep on going forward. Okay, so that is the reason we then have seat belts in cars. So we need an unbalanced force to stop your body from continuing with the forward motion. Imagine if the car stops, but your body, because you are not the car, these are two separate bodies. Okay, there's the body of the car and there's your body. The car stops, but your body continues to go forward. If your body continues to go forward, it means you are now going to go forward and hit the dashboard of the car, or you're going to go out of the windscreen, or anything can happen depending on how abruptly and how fast the car was moving. And these are things that have unfortunately happened in reality, okay, where people will be ejected out of the car that has suddenly stopped, okay? And the reason is because there was no unbalanced force to stop them from moving. There was a force that stopped the car, but there was no force to stop the body inside the car from continuing with the motion. Newton's first law says if you are moving, you are in the car and you're moving with the velocity of the car, and the car suddenly stops, your body will continue moving forward until an unbalanced force acts on your body. So that's why you need this unbalanced force to stop you from moving, because your inertia will resist the change in motion which happened to the car. So your body will still want to continue moving. Sometimes if you're not wearing a seatbelt, you'll try to hold on to things inside the car which are mounted to the car so that your body can stay within the car without moving further forward. Okay, so that is now the reason we have seat belts. Okay, seat belts are there to provide the unbalanced force and thus protect you from hitting the steering wheel or the dashboard or windscreen, or even at some extreme unfortunate situations for you from exiting or being ejected through the windscreen of the car. Okay, so this is the purpose of seat belts. Seat belts are there to protect you by providing an unbalanced force which will protect you from continuing with your motion, as explained by Newton's first law and together with the definition of inertia. Okay, so this is something that you also need to understand. I don't want learners to keep on losing marks when it comes to this particular question where they ask you, explain the importance of seat belts. They are there to protect you from continuing moving forward by doing what? By providing an unbalanced force that is going to pull you backwards instead of your body continuing to go forward. Okay. Let's wrap up today's lesson by looking at another worked example which I find very interesting, and this is one of those that learners tend to struggle a lot with. Okay, in this worked example, we have an object which is placed on an inclined surface. As you can see, we have an object of mass 2 kilograms and it's placed on a rough plane. We know that as soon as we see the word rough, it means there is a force of friction or a frictional force. And then we are told the angle between the surface and the horizontal, and then the object remains stationary. As soon as we see the word stationary, we now think about Newton's first law. Okay, every time you see the word and the object, especially in questions that have to do with Newton's laws, that would be your question 2 of paper 1 if you're in grade 12. Okay, you know for sure as soon as they say the object is stationary, it means that F net is equals to 0 there. Calculate the frictional force acting on the object. You see, now it's important for you to go back to the knowledge of free body diagram, because here you have to understand which forces are acting along the same line and which forces are responsible for the object remaining stationary and not moving. Because our understanding is that if this surface was smooth, and you put an object at the top there, the object would slide down. Okay, but in this case, this object is not sliding down. We are told that it is stationary. It's not moving. It means there are forces. The forces that are acting on this object are balanced, or they are cancelling each other out. If you were to draw a free body diagram of this thing, what this would look like, of course, there would be, I'm going to break down the weight into its components. Okay, we know that the weight will have a component called Fg parallel, and it will also have a component called Fg perpendicular. This is based on what we learned in the previous lesson. There will also be, because this is in contact with a surface, there will also be a normal force, and there will also be a frictional force which is up the slope, and I'll explain just now why I drew it up the slope. Now, you know that this object remains stationary. For the object to remain stationary, it means there must be a cancellation of the forces acting along the same line. The forces that could be responsible for the motion of this object can only be Fg parallel and F, which is the frictional force. Those are the only forces that can be responsible for the motion of the object, because the object will either move up the slope or down the slope, since it's in contact with the slope or the surface. All right, the normal force and the Fg perpendicular are not necessarily responsible for the motion of this thing. Okay, of course there is a relationship between the normal force and the frictional force, which we learned in lesson 1 of this particular topic. All right, okay, so in this case, what do we know? We know that F net will be equals to, we are going to focus on the forces that are acting parallel to the slope, because those are the forces responsible for motion if there is motion. F net will be equals to 0. What will F net be? F net in this case will be Fg parallel plus, okay, not equal to, plus the frictional force. These two are going to add up to 0. Again, remember I said we must choose a positive direction. If we choose down the slope as positive, or it doesn't matter, you can choose down the slope as negative, but let's choose up the slope as positive is also fine. Let's do this for a change and say down the slope as negative. What then happens is that in your substitution, it means this force, the parallel component of the weight, must be negative because it's going down the slope. So in our substitution, what do we know? We know that this is mg sine theta. Before we substitute, let's just simplify this thing so that it becomes easier as we go forward. Okay, mg sine theta is actually Fg parallel. Okay, so when now we then come and substitute here everything that we know that this is a force that is going to be going down the slope, and down the slope is negative. So this will be negative m is 2 times 9,8 which is our g, multiplied by sine 7 plus frictional force is equals to 0. Okay, so we're going to then go to the calculator and check what the calculator says with regards to our substitution. Okay, in our substitution, I'm going to say negative 2 times 9,8 times sine 7. Okay, that's what we have there. We get the answer to be negative 2,388. If you round it off to 2 decimal places, it will be negative 2,39. Okay, so this will become negative 2,39 plus frictional force is equals to 0. This therefore means the frictional force is equals to 39 newtons. Okay, so this is our final answer for the frictional force, because that's what we are asked to calculate the frictional force according to the question. And because our answer is positive, remember what we said up the slope as positive, it therefore means our direction will be up the slope. Okay, please do not say upwards, because upwards means vertically upwards. So just say up the slope, and that is how we answer the question on this particular worked example. Again, I'll emphasize what I've been saying in the previous lessons. The best way to keep your understanding of this thing is to do more and more practical examples and questions on these particular topics that we've covered. Okay, I hope that you have been empowered. This has been Butho Academy, Newton's laws, lesson 4, and today we're looking at Newton's first law. In our next lesson, that will be lesson number 5, we are going to be looking at Newton's second law, which is the learner's favorite and the examiner's favorite, Newton's second law. Okay, please do not jump into laws without understanding the forces, and please do not jump from one law to the other without understanding the previous one. You do yourself a big favor if you have a proper understanding of the first law before you go to the second law. Okay, we meet again on lesson 4, and we are going to be looking at Newton's second law. In the meantime, let us practice as much as possible. This has been Butho Academy, lessons that empower, and I hope that you feel empowered. Till we meet again. Thank you.